Hello, I'm Nancy Perlman. On this edition of ECONEWS, we travel to San Basilio Bay near Loreto in the Mexican state of Baja California Sur. This scenic area along the wild and remote rocky shores of the Baja California Peninsula faces the Sea of Cortez, more commonly known as the Gulf of California. During this excursion, we join Williams College Emeritus Professor Marcus Johnson. He shares with us his many discoveries of unique geological formations and fossils that illuminate millions of years of placid seaside environments interrupted by cataclysmic volcanic upheavals and violent storms. Our destination is an isolated bay on the Gulf of California. From the nearest town, Loreto, in Baja California Sur, Mexico, visitors must travel overland on Mexico Highway 1, a distance of around 36 miles, approximately 58 kilometers. There, a dirt road leads east to the coast. This road requires a four-wheel drive vehicle. At the end of the track, the Gulf of California comes into view and visitors see the stark beauty of San Basilio Bay. Pristine, tranquil, San Basilio Bay presents a unique site for the study for the geology of volcanic eruptions, ancient sea life, and the continuing forces of weather and waves. Visitors may travel northward along the coast, a boat journey of approximately 19 miles or 30 kilometers. Rising 26 feet from the sea, only the rhyolite spires remain of volcanic eruptions millions of years in the past.
I'm Marcus Johnson, Professor Emeritus at Williams College in Western Massachusetts. I'm quite a long way from Massachusetts because we're here at San Basilio Bay in Mexico's Baja California. We're on the east coast facing the fabled Sea of Cortez, otherwise known as the Gulf of California. Landscapes are an inherent attraction for a geologist, and there are several stages in understanding what a landscape means to a geologist or to the public at large. A landscape can be picture perfect, and behind me we see a very calm area in this bay that represents a feeling of calm, a feeling of safety, as it were. But to a geologist, we see other aspects that make a landscape even more beautiful when we attach names to the kinds of rocks that we see in the background. This gives a more complete knowledge of an area. But even more beautiful is the idea that sometimes we have to struggle, we have to grasp for a meaning. And it makes it even more intensely beautiful because sometimes it takes time to understand a particular landscape. We've now climbed down the rock face to get closer to the geological action, and we're about to attach some names to the geological structures that are here. Two of the most iconic structures in the entire San Basilio Bay are right at our feet. We're going to start by looking to my left and noticing that these rock layers are perfectly horizontal and stacked up. These are limestone layers, and they're formed by organic material that is accumulated gradually, layer by layer, through time. The predominant ingredient of this limestone is formed by pecten shells, commonly known as scallops. When we look to my right, we see initially this flat limestone layer suddenly ramps up skyward. That's a very unusual structure, not easily understood. Now, further beyond this limestone, we see a second type of rock. It's an igneous rock, it's a volcanic rock. We're looking at the filling of a throat of a volcano. We're looking at a volcanic neck. The name that we're going to apply to these rocks is rhyolite. It sounds strange. It's a name that most people won't recognize, but in fact, it's very closely related to granite, a more common name that most people recognize. The difference is that a granite is formed deep below the earth in a magma chamber, and that magma that stays in the chamber will cool very slowly to form recognizable crystals, often dominated by silica. But in rhyolite, which is chemically exactly the same as granite, is a very fine-grained volcanic rock. I'm now standing on the lip of a natural basin where seawater could accumulate and dry out under the sun. To my right, we see the ocean, and during a storm, waves would wash up over this natural rise and flow into this basin. Over a period of days, in intense sunlight, the seawater that ponds here is slowly going to be able to evaporate. When 9/10 of the water is already gone, that's when salt, NaCl, common table salt, begins to form as crystals. When we look down to this whitish area, we see actually quite large crystals of salt, which form in a cubic nature, perfect little cubes. If we pause and take a finger and dampen it and reach down and bring it back to the mouth, the taste of the salt is unmistakable. This is a very slow process that only develops as the seawater is slowly evaporated away. The same waves that are bringing salt water into this salt basin are slowly undercutting the limestone platform that we're standing on. Eventually, given enough time, these slabs of limestone will fall into the sea, and this bridge will be completely eroded away. But this is going to take thousands of years to happen. So happily, this iconic structure is here for the short term for people to enjoy. We've now advanced across the flat part of the limestone bridge, and we've strolled up what I call a ramp, the limestone ramp. It's a very unusual change from the flatness to a ramp. To my left, we actually see the highest part of the ramp exposed behind me. It's quite a difference between the elevation of the flat limestone and this upward part of the ramp. We're actually looking at about a 12-degree slope from where I'm standing down, across, and over to the bridge. The question is this a natural phenomenon or some other type of phenomenon related to the regional tectonics? Behind me, we see the spires, the volcanic spires. And our challenge is to connect this ramp to the volcanic spires. The landscape here is beautiful on its own account. And we've tried to establish some names that bring more meaning to the landscape, the different types of rocks. I'm sitting on the limestone, the very pectin-rich limestone. Behind me, out of sight, is the rhyolite that is stuck inside a volcanic neck. The problem is to try to connect these two lithologies. What is the relationship? Are they in fact related? Here to my right is a gray-looking rock which happens to be rhyolite. It's a it's a boulder. It happens to be about 50 centimeters in diameter. How did it get here? How could it possibly get here? In geological terms, we call this a bomb. It's a volcanic bomb. When the volcano exploded, it ripped off parts along the inner throat of the volcano and cast those high into the sky. Imagine then what it would be like to be sitting on this seafloor with a volcano behind you, maybe a football field or less away. You might feel the rumbling. We're underwater. We're surrounded by pectin shells on a slope, but all of a sudden around us, it's like being in a military zone. There are bombs dropping everywhere around us. There are rocks that are falling into the water, making a splash above us and sinking to the bottom. Now the casualties are okay because these pectins are already dead. There are no live pectins here. But we get the feeling, we might even feel the vibration of the volcano behind us. Here we have a meeting point between the limestone and the rhyolite because we have the rhyolite interjected into the limestone. I'm sitting below a lip of overlying limestone while sitting on another limestone, and in between we have 2 or 3 feet of volcanic ash. It tells us about a sequence of events, starting with rocks being ripped through the throat of a volcano and making the bombs, followed by another explosion, an ash explosion. The ash is sent through the air and actually lands on the water and penetrates like a curtain through the water. The ash, we have a recession here because the ash today is quite soft and it erodes very easily. That's why we have a kind of a gap here between these 2 layers of limestone. The water would have been quite milky and visibility would have been quite low, and we would want to swim away from this area as fast as we could. We're now standing at the very lowest layer of the limestone ramp, angling up at a rather high degree towards the volcano. What we see here are a series of limestone ribbons, as it were, composed of really rich concentrations of pectin shells. This is basically a necropolis. These shells didn't live here. They're already dead. Each ribbon represents probably a separate storm that appeared that washed against the slopes of the volcano and caused a cascade or an underwater avalanche that fell down the slopes of the island, the little islet. Each one of these ribbons is about 3 to 5 inches thick. Then there's a period of calm, nothing happens, and then another ribbon and another and another. We're seeing a cross section now of the carbonate ramp. We're at the bottom because the whitish layers that we see beneath the limestone represent the rubble along the skirt of the volcano that also came down. We're looking therefore at the very earliest representations, the very earliest stages of the limestone formation.
This illustration shows a cross-section of the limestone ramp and the volcano rhyolite millions of years ago. Over the eons, billions of pectins formed limestone against the volcano.
The limestone ramp that is so iconic to this landscape in San Basilio Bay is slowly dissipating through natural erosion. Behind me, you see an enormous chunk of the ramp that has fallen off, probably during an enormous storm when waves were crashing into this structure. So the fallen piece actually represents the apogee, or the highest point that we can see of the ramp structure. Approximately only 10% of our carbonate ramp exists today. The rest has been eroded by storms. Across the bay, however, we see a second set of rhyolite spires that are embedded in the cliffside. Not only do we have that spire, but we have a third spire standing in the water as a sea stack, totally stripped of its limestone skirt. We're located about a half kilometer north of San Basilio Bay. I'm standing on a very unusual rocky ridge with enormous boulders that are composed of rhyolite. This locality is unusual because of the fossils that are contained in amongst the boulders. For example, I'm holding a shell called Periglypta multicostata. It's a shell that's quite old. In this case, the fossil itself is about 4 million years old, but the same species is found today all the way from the Gulf of California down across the equator and into Peru, but always in a rocky shore setting and always in very, very shallow water, and always the clam is nestled in amongst large boulders. This means that the locality we're describing is quite different from the pectin localities, the pectin shells described earlier, that were basically a dead deposit. So this is a deposit that's reflecting a real environment in its natural state with what were living species preserved intact. These large boulders are cemented in place, firmly in place by limestone. And in the direction to my right, to the west, it was increasing in water depth. The shoreline would be to my left.
While walking around this coastline offers a close-up view of the geology, our drone footage gives us another perspective of the landscape and a penetrating look of the geology hidden by the water. From the air, the drone camera shows the rhyolite spires surrounded by the broken stone of eons of hurricane wave action and erosion. A storm passed on September 14th, 2014, as a Category 3 event. Winds of 70 miles per hour hit San Basilio Bay. Observers on the shore saw waves overtopping the 26-foot-high spires before crashing down on the limestone ramp. These storms cause a gradual erosion of the shoreline. Here in our aerial view of the San Basilio rock spires, we can see that almost all of the limestone skirt that once encircled the former volcano has been stripped away. The top of the limestone ramp has already suffered extreme erosion. As storms continue to come over time, the rhyolite and limestone formations will disappear. Near San Basilio Bay, north of Laredo, in Baja California Sur, Mexico, is Clam Bay, or Ensenada Almeja. Geologically, this area speaks to the region's propensity to absorb major storms that continue to this day. Williams College Professor Emeritus Marcus Johnson explains the unique geological elements that give pause to our thinking about patterns in global warming. Over Clam Bay, this drone imagery shows an immense boulder deposit arrayed in a semicircular pattern from the sand of the bay to a bedrock ridge.
We're here at Ensenada Almeja, otherwise known as Clam Bay. We're located about 1 kilometer due north of San Basilio. The reason we're here is to look at another kind of rhyolite. The rhyolite at the center of the volcanic neck at San Basilio is fractured different and has a different appearance. This is called a banded rhyolite. It has the appearance of a kind of plywood, very, very thin layers. But you'll notice that the material above my head is contorted in a different sort of position. This is because the material, as it oozes out of the earth, has a taffy-like consistency, making it easy to sort of flow over each layer and form these very interesting structures. I'm walking along what looks like an outer wall composed of boulders derived from the same banded rhyolite that we looked at just previously, but they're forming a solid wall. These boulders are some really large blocks of material. The shape of this outer wall is arcuate, maybe about 500 meters in length. How did this form? What does it mean? It's a real paradox to sort of figure out what is going on here. The rocks become larger and larger as we go towards the point of the peninsula, where we have solid rhyolite rock. And indeed, some of the largest boulders are over in that direction. So where did these boulders come from? They had to come from the basement rock, the banded rhyolite. That's the only place they could come. They couldn't come from across the bay, and yet this distribution is very odd. Behind me is a due north direction. This is to the east, this is to the west. And yet these boulders form this semicircular pattern, becoming smaller and smaller as they go back towards the south. We're now standing at the point of origin of a major coastal boulder deposit. To my left, we see the actual place where these boulders are being eroded out of the cliffside. We have a natural vertical joints in the banded andesite, and we also have horizontal bedding planes. As a large wave, as in a hurricane wave, strikes this surface, it begins to mine out these blocks, which will tumble into the water and form initially just a few feet or meters away to my right. Some of these blocks are enormous in size. The largest block that I've measured here is 8 feet in diameter. The kind of wave that would be necessary to move such a block would be enormous. 30% of the blocks in this area are large enough that they register at about 2,000 short tons. The wave height of a wave that would be necessary to pick them up and move them is about 8 meters. That's a very large wave. The way that we calculate the tonnage is by knowing the volume of the rock, which can be measured directly, and the density of the rock. And a very complex mathematical formula is then used to calculate the wave height necessary to move those blocks.
I think that's a good place for it right there.
Okay.
Chisel, little chisel.
Many storms over many thousands of years produced the Clam Bay boulder arc of boulders. These video images show the professor and his friends affixing permanent markers on boulders to determine how much the next storm waves may shift the boulders.
Oh, that's number 6. Are you getting this?
Yep.
I got that
Well,
already.
okay. Get a little bit, just a little bit on that little corner
Well,
there.
I'm going to put some on the edge of it when we put it on.
Okay. All right. Guide me in now.
Right here.
Right here?
No, right down
There?
Yeah.
I hope that you have enjoyed seeing the beautiful landscape along the Gulf Coast and bays in the middle part of Mexico's state of Baja California Sur. I look forward to again visiting this area of the fabled Sea of Cortez and exploring more of San Basilio's and Ensenada Almeja's unique natural and cultural history. On behalf of ECONEWS and our nonprofit organization, Educational Communications, I'm Nancy Perlman, wishing you a natural, unspoiled environment.